talk today, guys. We're going to speak about Bayesian workflow and statistical modeling as craft. I'm going to use a case study of structural equation modeling with job satisfaction data. So sort of preliminaries, for myself, I'm a data scientist at Personio, primarily a Bayesian statistician, open source contributor to PyMC. There is code for this. There's a PyMC examples notebook, which I've added to the Discord chat there. If you follow the QR code, you'll find my website where most of the stuff is as well. So that should be fine. The broad pitch for this talk is that probabilistic programming languages are a really useful tool for expressing uncertainty, building relationships between statistical models, and structural equation models are a way to formalize a sort of scientific theory as a set of statistical relationships. And the argument is that the Bayesian workflow will bind these two things together in sort of a compelling practice. That is a conversation between theory and data, which is sort of disciplined by the rigors of probabilistic programming and the requirements thereof. So the agenda for the talk will be kind of broadly as follows. I'm going to introduce sort of opposing views of sort of statistical workflow. Somewhat caricatured, but I'm going to have a good guy and a bad guy, sort of. Then I'll talk a little bit about the job satisfaction data we're going to explore. And then I'm going to step through what the sort of contemporary Bayesian workflow looks like when applied to a structural equations modeling problem. It's going to be sort of iterative and expansionary, and we're going to start simple or relatively simple with a confirmatory factor model, and then step that up into a sort of more elaborate structural equation model. I'm going to talk a little bit about sensitivity analysis and hierarchical versions of structural equation modeling and parameter recovery validation checks. And then we're going to conclude with sort of a reflection on the value of craft in your statistical workflow. I hope that's broadly clear from the thrust of it. If there's a really pressing question, feel free to interrupt me throughout, but otherwise I'll try and get questions at the end as well. So the idea of a workflow, so what I want to say about craft and statistical modeling is that to take a craft view of statistical modeling is to embrace the process, to accept that there's going to be imperfection in each iteration and that you need to iterate. The aim here is broadly the acquisition of scientific knowledge, which supports generalizable findings and solutions, and will restore sort of ownership or to your work, like the model you're building will carry your imprint. So you'll develop a sense of pride or ownership over the work. In contrast, so this is the bad guy caricature somewhat slightly, is that statistical modeling can be seen as a sort of checklist exercise or a ticking box exercise. It's the opposing view. And I'm going to argue a little bit that this approach to like checklist statistics sort of creates an illusion of rigor while bypassing the actual work. It confuses progress with throughput. Boxes checked is not better science. And I think this is important if you're working in industry. It sort of promotes a shallow level of engagement from your stakeholders, from your management classes, and this ultimately hinders effective decision makings in your organization. It also strips away ownership from you. You're not building something, you're just completing a task. So those are the two contrasting views, and I'm going to argue for the first one a little bit. The data we're going to look at for this case study is a job satisfaction data set. It has 12 indicator variables. These are survey responses scored, I think, between 0 and 5. And they're kind of trying to gauge 4 distinct practices or views of the respondent, right? So the respondent in these surveys are scored, say, on their self-talk, their propensity for mental imagery, their propensity for evaluating belief and assumptions. They're also scored on other indicators for dysfunctional thought processes, their subjective well-being, and their job satisfaction. What's at the heart of this analysis is we're trying to figure out what the effect is of constructive thought processes, like evaluating beliefs, assumptions, your tendency to visualize things, has on your ultimate job satisfaction. Okay. We're going to apply the sort of contemporary Bayesian workflow, which is sort of made famous by Andrew Gelman and Cosma Shalazi. There's a nice paper on it. We're going to use modern tools like Arviz and PyMC. But the broad thought for the contemporary Bayesian workflow is to start with your theory and your prior knowledge, iterate with checks and visual diagnostics, refine the structures of your model as you encounter obstacles, you want to improve it. You're assessing consistency of signal across multiple iterations of the same model, and you want to validate through a sensitivity analysis, which is not necessarily exhaustive, but at least compelling. And ultimately, you want to own the process. You want to be able to claim that the end result is a compelling model that withstands the scrutiny of various types of validation. Structural equation models. So these are broadly thought of as very richly parameterized regressions. The SEM workflow, as I said, is sort of iterative. You're going to start with a confirmatory factor model. I'll speak a little bit about what a confirmatory factor model is in a second, for those of you who haven't heard it. You're then going to add complexity to that by laying on structural relationships between your latent factors. The latent factors that we're interested here are that measure of job satisfaction, that measure of well-being, or that measure of how well your sort of constructive thought processes work. They are abstract factors, not directly measurable. The whole point of the structural equation model is to say that we have this somewhat abstract notion that we can poorly approximate through a range of survey measures or other indicators, and we're going to derive a latent factor to reflect that construct. Once we've established the constructs, we layer on the structural paths, i.e. regression relations between them. We can add structure to the errors of our model, so like your epsilons, and then we can iterate and validate and I'll visualize this a little bit so it'll become a bit more concrete rather than just like abstract, right? But like I said, our data set looks like this. We have 12 indicator variables. They're sort of grouped here, color-coded in this setting to indicate which three load on which of the latent factors. So the blue here, JW1, JW2, JW3, are our scores of a job satisfaction question in our survey data. And we want to take those three measures and sort of derive a measure of an individual's job satisfaction. Okay? So in a diagram, this is what a confirmatory factor model looks like. We have 12 indicator variables here. They each are determined by, or so goes the argument, this latent factor, which drives them. So the arrows come from the factor to the indicator variables. In the statistical model, we're going to say that there is a factor loading parameter, which is a weight applied to the observed data, so the indicator measures, which determines how strongly that predicts or is predicted by the latent factor. We're also going to model within our model these red arrows, which are the covariance relationships between the latent factors. So we want to understand at a high level, how does job satisfaction move with dysfunctional thought practices? How does well-being move with job satisfaction? Okay. In code, what we're doing here is deriving, so the arrows here are determined by parameters called lambda in the literature, right? So these are effectively like regression weights, but in the literature they're called lambda. So this is the matrix of lambda coefficients that we're kind of interested in, and they're going to load on the observed data that we had, so the 12 variables we have. So we have one lambda term for each of the 12 variables. That's going to be processed in PyMC, basically in a simple enough matrix multiplication, and then we're going to get conditional values, expected conditional values for the observed data points in our original data set. We're going to feed them through a likelihood term for the Bayesian model. We're going to update in the Bayesian fashion. That's a whole other topic that we don't need to talk about today, but we're basically feeding data through this parameterized model. We're updating it in a way to learn the values of these latent coefficients, these lambda parameters. And what we get out of a confirmatory factor model then is, I tried to pull all of this into one image, but basically at the top here we have, so our data set is like 1,200 observations, and there's basically 1,200 draws for each of the latent factors, right? So we have an individual's satisfaction score. We have an individual's well-being score. We have an individual's constructive thought process score, and we have an individual's dysfunctional. Like they're all scored on this agglomeration of the three indicator variables per factor. We also get the parameter estimates for each of the factor loadings, so each of the lambda terms. And what's important to note about these is that the lambda terms are sort of scaled to an observable variable. So in the model here, the 1, which is fixed, is a fixed value. So the latent factor now has a defined scale, and the scale and the magnitude of that scale is determined by the first indicator variable. So what's important when you're looking at a confirmatory factor model is that the factor loadings are broadly close to 1. Because if they're like all of the same scale and the same magnitude, it supports the argument that the indicator variables load on your latent factor in similar, equally commensurate ways. It's another way of saying that you have measured the latent factor well via these three indicator variables. Okay. And the final plot at the bottom here is probably the most important one for model assessment. So when you're thinking about a factor model or a structural equation model, what you generally want to ensure the model does well is capture the covariance structure between the 12 observed variables you have to hand. So the plot at the bottom shows the residuals between the model's implied covariances between the indicator variables and the observed covariance structure in the data set. And so the closer to 0 that those values are, the better your model has captured the covariance structure of the original data. So this is a confirmatory factor model. White is close to 0 here. There's some highs, there's some lows. We could do a bit better, right? But that's like a sort of array of ways to look at what your model says about the data that you just fit and how well it captures that data you fit. So I'm going to move quickly on. I'm going to talk now a bit more in detail about the structural equation modeling part and what that does. But fundamentally, the same type of thing is happening at each iteration here. We're fitting a new model with some extra structure or values or whatever, and we're going to assess it for validity, coherence, or consistency with the previous values seen. So a structural equation model is built on top of the CFA model you saw before, but now we add arrows. So those are the blue arrows here. And the arrows are sort of regression relationships between the latent factors. So we want to add a predictive dimension. We want to say that the measure of constructive thought processes that any individual has is somewhat predictive of their dysfunctional one. So ideally, if high for constructive thought processes, you're low on the dysfunctional thought process. But it's also a predictor to some degree of well-being and ultimately job satisfaction. So how do we specify that? Basically, it's matrix multiplication again. But what we do here, instead of a beta coefficient, like a set of beta coefficients, like in a regression model, you build a B matrix. And this is a matrix that you're going to put a little bit through some sort of fancy matrix multiplication, but you're going to basically say, like we saw here before, that we want to predict satisfaction as a function of well-being, dysfunction, and constructive thought processes. We want to predict well-being as a function of dysfunction and constructive thought processes. And we want to predict, what's this one? So last one. It's dysfunction as a function of constructive thought processes. But nothing predicts itself. Yeah, so that's the regression specification. It's done in a matrix format. What we get out of it is those values for the draws on the latent factors I described before. So the top of this plot. We're predicting each of these variables in this system. It's a system of simultaneous equations, and to derive the estimates for the B coefficients in our model, we need to do this solution. But we get out of it then those latent scores with the predictive relationships contained in the model. We can add more arrows, so predict one and then predict the other, so we have a chain of mediated predictions. And we can add yet more again, and we can add more structure to add residuals. Right? This is like a really rich way to express relationships between latent variables in the model. Because arguably, we're often more interested in the latent construct than we are in the observed indicator variable, which we take to be generally a poor proxy on its own. That's the kind of heart of the motivation for SEM modeling in general. So in the PyMC context, what this looks like, similar to the CFA model you saw before, but now I've bundled that B matrix into a make B function here. But we basically take the make B function, we solve it, and then we get another estimate for our latent constructs, so the conditional expectations of the observed variables. We again feed that into our likelihood term, but here we're using a multivariate normal likelihood with a specific covariance structure, which has taken in the residual covariances in the model specification that you saw here. So we have a covariance structure that we've explicitly allowed positive or negative correlation between those two variables. So yes, have I moved too fast? I moved too fast. Yes, so basically what we get again after adding these structural paths, similar latent draws as before, but we get new coefficient values. We get coefficient values for the beta regressions, right? So we get a view of how important constructive thought processes are for predicting well-being. We get a view for how predictive they are of job satisfaction, which I will come back to the values that we're seeing in a minute. We also get an improved residual plot at the bottom. Having added this extra structure, we have more white space on the bottom plot. We're closer to reproducing the covariance structure of the observed data, which is a health check or a sanity check that we're doing something sensible by adding all that extra regression structure into our DAG. I'm going to breeze through this one. This is a third iteration of the model with some more structure, but I think I've belabored the point a bit too much. The point we want to get at is there's more structure you can add. There's another mathematical formulation to derive more efficient sampling. I don't think we need that now. Basically, I get an equivalent model, but I've added more structure, so it's kind of needless structure. So like that's an excessive move that I don't need and should kind of remove from my model. So sort of sensitivity analysis. What we've done now to reflect on is that we fit 3 different models with subtly different structures each time, but they were all sort of targeting what is the relationship between job satisfaction and you make sure you give me a 5-minute warning, just between job satisfaction and constructive thought processes. So what we kind of want to review now is like a sort of sensitivity analysis to ensure that like we're getting sensible measures along the way. So what you see here is sort of like a comparison of the 3 models we fit, right? And on the bottom, which we should start with first, we have the factor loadings. So those are the sort of lambda coefficients that we fit in all 3 models. And the important thing to note with this is that they're basically the same across all 3 versions of the model specification. So by adding extra structural equations, like solving the simultaneous equation, we have not changed the latent factor loadings, which is, it's good time. For the last 2 models we fit, we estimated the sort of weights of sort of well-being and satisfaction, dysfunctional thought processes and satisfaction, so on. And we can compare these 2 models on those measures. And the broad thing to highlight here without going too deep into the individual values is that it's basically a consistent pattern across both models. So constructive thought processes do have a positive effect on job satisfaction for both models. It's not huge, but they do have it. Far and away, the biggest predictor of job satisfaction is your individual well-being, which should not really be a surprise to anyone. As long as you're getting a paycheck, you're generally going to be happy. So these effects, because it's a structural equation model, you can look at them individually on the one-to-one relationship, but you can also look at the indirect and direct effects. So this is sort of like a view of the total effect of constructive thought processes as mediated through the three latent factors. So you can kind of see here, the direct effects would just be your beta coefficient in a regression. So it's like constructive thought processes have a 0.06 positive effect on satisfaction. Indirectly, via the relationship with well-being and dysfunctional thought, it has a net positive 12 effect. So is that clear? So you have more paths, so you can trace all the pathways through all your latent factors, and you can gain a more nuanced understanding of how constructive thought processes operate on your variable of interest, i.e. your job satisfaction measure. And this is all kind of comes for free with that B matrix, basically. Okay, so variations on the theme here. So you might want to challenge or like question the consistency that we saw on those beta coefficients or those B weights. So one natural way to kind of interrogate that is to say, well, I don't think that the relationships between sort of constructive thought processes and job satisfaction are going to be the same across like experimental units, gender, job type, whatever kind of group indicator you want. You might reasonably question or check whether or not we would expect consistency across those types of different heterogeneous types of people or units, right? And one way to do that, you can sort of model that again by allowing a hierarchical form of a structural equation model. So what that does is you take the same structure as before, but you allow for sort of multiple parameterizations for each individual group. So you can allow that the relationships between constructive thought processes and your sense of well-being is different from men versus women. And that means that you make your model more complex, like significantly more complex, because you get n new parameters for each group you add, right? So in this case, say we add 2, we have 6 regression coefficients, so we have now 12 parameters instead of 6. I'm not going to dwell on the code. It gets more complicated, but you're basically doing list comprehension across the groups. Solving again, and then feeding it into your likelihood term and estimating. So with complexity, you can reasonably challenge whether you're doing something sensible, right? Like it's a hard thing to sort of go to your stakeholders and say, I have like this model with 1,200 parameters, and let me assure you these 10 parameters are the ones you care about. So you want to be really sure that you haven't added complexity needlessly, and that your complex model can recover the accurate treatment effects or accurate parameters of interest. So one way to do that in the sort of Bayesian workflow is to do a parameter recovery exercise. So in this case, what you're doing is you're specifying the parameters that you're inputting into the model. You're forward simulating with this do operator in PyMC. So like you're setting the values of the parameter model, you forward sample, you draw from the prior predictive distribution. And you take that synthetic observed data, synthetic data, so to speak, and you put it back through your model and estimate the posterior distribution of the parameters. And what you want to recover then is parameter values that match quite well with the parameter values you set in the initial data generating condition. So basically, at a high level, what we've done here is fit multiple different models to the data. We've checked across the different model specifications for consistency and performance, made sure that directionally the parameters made sense. We've ensured that the model is well specified or specified well enough to recover accurate parameters. It can identify the parameters of interest. And that all of those things are like iterative, expansionary, step on the way to understanding. And that's characteristic of modern Bayesian workflow. And so what I'd like now to sort of like, now that we've absorbed all that, is to sort of reflect briefly on the value of craft in statistical modeling and in workflow. So, and I want to draw an analogy between statistical modeling and writing. And I want to take this guy, Verlin Klinkenborg. He has kind of a really nice little book if you're into that kind of thing. Several short sentences about writing. So the prompt here is that you should think of your models or your sentences as conjectural. You fit them, you expose them to data, you see what the implications are, you check them on the go. You don't presume your outcome in the specification of the model, so to speak. It is a process of discovery, and you need to follow that process to build models well. Modeling is like writing. It is an act of exploration. You should expect surprises and anomalies because they teach you more than preconceptions. You should embrace uncertainty in the process and allow the data to be somewhat of a guide to your process. This is a quote from Gelman and Shalazi on the same. We're going to make sure that our models are fundamentally iterative and expansionary. We should be learning from our models all the time. If they can't generate synthetic data that looks like the real data, this is a failure and it indicates faults in the models that we need to correct for and learn from. So building statistical models is inherently iterative and expansionary. The assumptions that we encode need to be assessed for their implications. And when those assumptions fail, we need to revise or reject them. And this whole process will build confidence and clarity in our understanding and in what we can kind of bring back to the business or the world in general. So this process should yield compelling and justifiable conclusions worthy of your effort. This is the closing quote and conclusion. So this is from Klinkenborg again, but I think it's a beautiful, concise, and lovely message. So here in short is what I want to tell you. Know what each sentence says, or what each model says, what it doesn't say, and what it implies. In modeling, writing will emerge through revision, or clarity will emerge through revision. The Bayesian workflow with PyMC teaches us to listen to their model, read them aloud through simulation and parameter recovery, and critique. Each iteration reveals what the model truly says, what it hides, and what it implies. And craft lies in that attention and resisting the flattening automation and choosing understanding over throughput. And through this care, our models become not only more compelling, but more robust, and resilient to noise, misfit, and misuse. Thank you. I think I have like 5 minutes for questions to start, so if there's any.
I have a question. How large is the sample size for the data set?
So simulation data. So I tested multiple, but 10,000 rows. So, but it works on like 2,500 as well. So you can scale up and down.
So you have 12 variables, all latent constructs.
Yeah.
So 3 variables for each latent construct. Are there any reasons? Or 3 for.
So the data set is not mine originally. It's I forgot the name of it. It's like multivariate statistics in the social sciences. There's a paper which has these 12 variables in it, and they don't actually provide the data set, but they give you the covariance matrix, so you can kind of replicate it yourself, which is kind of annoying. But the data is from the literature, not from my head, so to speak. So, but I do think like having 3 variables per factor is very convenient because it's like the minimum you need.
Now, here's things good. If you have only 12 variables, like say, the most important outcome is the job satisfaction. That's 3 variables. I was thinking if you want to simplify your analysis, let's say collapse the 3 variables on job satisfaction into a composite variable, and then you can run basic regression analysis. That is much easier to work with, much easier to interpret. If you think of it that way, because I don't go against the structured gradient model. I think it's beautiful, and you use it to get published. If you're in something simpler, and they might not accept it, but from like say, if you depend on the audience, if you want to explain things in plain language, I think a regression model might work well. With 12 variables, unless you have like 100 unknowns of variables, then so I can probably use.
So I agree. So like the broad thought of SEM in general, like is that your indicators have so much measurement noise, you need to collate them in some way or some. And if you just take the mean or the average, that's also an assumption about the collation mechanism, right? So that's fine, give or take. But I agree to your point about like how talking about these constructs is not necessarily tractable for the general stakeholders. So in the case study, if you follow that, I actually go more complicated yet again. So on top of the SEM model, I build a discrete choice model, which has the outcome of like stays in the job, quits, or quiet quits, right? So it's a much more tractable outcome if you're going to talk to stakeholders. You're not going to talk about the latent construct moved X, Y, and Z. You're going to talk about the job outcome, the stay, quit, or whatever changed or it's predicted well by these latent factors. So the stakeholders shouldn't have to care about your latent factors, but they should care about the downstream outcomes, which are very tangible, like whether the person stays in the job or not. So I think that is to accept the spirit of your critique, but say, I think there's still a role for a structural equation model. Anyone else?
Check the next situations. So I'm satisfied with my job because I'm happy with my job. Satisfied with the job
So that's fair. Like, I mean, and that's going to kind of determine which way you draw the arrows, right? Like, but you're making an argument when, well, in general, when you're doing causal inference for kind of complex statistical models, you're making an argument that the way you've specified the structure of the model is the most plausible one, or it is the one worthy of interrogating. And so the way I drew the arrows here, sure, totally contestable. You could draw it a different direction, but then you're interested in a slightly different question.
Leadership is unhappy. Question that. Others, I want to harsh the problem. You about this organization.
I mean, I think that's a mixture of politics as well, right? Like, I mean, if you're working in an organization that doesn't want to fix itself, then then either you need to be more compelling in your own delivery, or you're barking up the wrong tree, right?
Every organization is a physical organization. It's just to get through as it's leader.
Sure, but there are dimensions of like a political organization that still want to do the right thing. If you've run up against someone who doesn't want to do the right thing, then you're fucked from the outset, right?
You're screwed right.
This is just a tool for illuminating contestable structure in the data. But from a good faith perspective and an organization that wants to do the right thing, I think it's a useful tool. Okay, I think that's it, is it? Thank you very much, folks.